In the year 794, Kyoto City was chosen as the seat of Japan's imperial court. For over 1,000 years, it served as the royal capital of Japan, before the capital was moved to Tokyo. Although it's no longer the political capital today, Kyoto City is considered the cultural capital of Japan, so it's a major tourist destination. Located southwest of Tokyo and near the city of Osaka, Kyoto City is known for its many cultural sites and traditional festivals. One of the big festivals held in the city every year is the Cherry Blossom Festival. For some, the beautiful cherry blossom is an iconic symbol announcing the arrival of spring every year.
Oh my god!
For others, the Kyoto cherry blossom is a canary in the coal mine, warning us of a self-inflicted dystopian future awaiting us all due to human-induced climate change. How is it that this innocent-looking flower can simultaneously generate so much joy and yet so much dread? And what does any of this have to do with probabilistic programming? Well, let's find out. Welcome to Dago.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. The bulk of the code for today's tutorial comes from the SR2 TuringPluto.jl GitHub repository. This repository contains a collection of Pluto notebooks based on Richard McElreath's textbook, Statistical Rethinking. I've taken the code and modified it slightly for the purposes of this tutorial. I provided a link to the source material in the description below. In the interest of time, I've prepared some code and an interactive Pluto notebook in advance. You can find a copy of my code and a copy of this Pluto notebook in my GitHub repository. There's a link to my files in the description below as well. If you want to follow along, you can save a copy of these files in a tutorial folder on your computer. After you save the files, in VS Code, launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square bracket. Activate the tutorial directory. Add the following packages: B-splines, CSV, data frames, stats plots, and Turing. Exit the package manager by hitting backspace. In the editor, execute the code to load the packages. Okay, now that we have our packages loaded, let's download some data. As a motivating example to help us learn about Bayesian B-splines, we're going to use a dataset prepared by researchers in Japan that provide a historical record of the full flowering dates of cherry trees in Kyoto City, Japan. Amazingly enough, the researchers were able to collect this data going all the way back to the 9th century by using diaries and chronicles written by emperors, aristocrats, governors, and monks who were living in Kyoto throughout the years. It's a pretty cool dataset, so let's take a look. I'm executing the code to download the data off the internet and into a data frame. If you're typing this code in manually, you can find a copy of this URL in the description of this video. If you click on the Julia logo icon and click on the table icon next to the df variable, you can see the data. This dataset contains 1,215 rows, and covers a time period between the year 801 to the year 2015. The column that we're interested in is the column labeled DOY, which stands for the calendar day of year, when the cherry tree reached full bloom that year. But since this dataset goes all the way back to the 9th century, this dataset does contain a lot of missing data, as you can imagine. So let's drop the missing data and prep it for analysis. Our dataset now contains 827 rows after dropping the rows with the missing dates. Okay, now that we have our data, let's take a look at it. In the plot, you can see that the cherry trees in Kyoto City have historically reached full bloom sometime between day 90 and day 120. For non-leap years, day 90 is March 31st, and day 120 is April 30th. The reason why this dataset is interesting is because the dates seem to fluctuate over time, but there doesn't seem to be a clear pattern. Because of the nature of this data, it's difficult to fit a standard function for a curve, like a sine wave. What we really need is some way to model these irregular fluctuations over time. This sounds like a good job for B-splines. The term B-spline is short for basis spline, which is a mathematical function that allows you to create custom curves. Rather than going through a formal definition, it's easier just to see one in action. In Julia, you can construct B-splines by using the bsplines.jl package. I've prepared this Pluto notebook to go through a B-splines demonstration. You can find a copy of this notebook in my GitHub repository. In this demonstration, we're going to look at a simple B-spline. In order to construct a B-spline using the bsplines.jl package, you need two things: a basis and some weights. The basis is a function definition for a flexible curve, and the weights are the parameters that you can use to bend that curve. In this interactive model, there are three weights that you can use to customize the shape of this curve. So when all of the weights equal 0, the curve is just a horizontal line. But when you increase the value of weight 2 from 0 to 1, notice that a curve appears, with the center moving up. When you decrease the value of weight 2 from 1 to -1, the curve flips, with the center moving down. So a positive weight will bend the curve up, and a negative weight will bend the curve down. Now weight 2 controls the middle of the curve. Weight 1 controls the left end. And weight 3 controls the right end. By changing the values of all three weights, you can create a lot of different curves. For this demonstration, this curve spans an x-axis range between 0 and 1, but you can scale it up to any range of values. In addition, you can combine individual B-splines together to create truly unique curves. These connections for these B-splines are called knots. That's K-N-O-T-S, as in connecting two strings together by tying a knot. Pretty cool, right? I know that I didn't cover a lot of code for this demonstration, but for now, the biggest takeaway is discovering that we can alter the shape of B-splines by changing the values of the weights. These weights are the most important input parameters that we'll be looking for when we create our Bayesian model. So going back to VS Code, let's enter in some of the code that we need to build our custom curve using the bsplines.jl package. For our datasets, we're going to use 15 knots, but you can increase or decrease this value if you like. The quantile function is from Julia's statistics library, and it takes your collection and returns a vector of values based on the probabilities provided. Click on the Julia logo icon and click on the table icon for the knots_list variable. This vector contains 15 elements for the 15 knots. The values are the calendar years in our dataset. By using these values, we can split our dataset into equal subsets, so we can evaluate them separately. With this information, we can create the basis by using the bspline basis constructor from the bsplines.jl package. Again, the basis is a function that defines a flexible curve. When using the bsplines.jl package, the order of the basis is 1 plus the degree of the b-spline. So by using 3, we're saying that we want a second degree b-spline, or a quadratic curve. Okay, we now have everything that we need in order to build a Bayesian model by using the Turing.jl package. By now, the format of a Turing model should look familiar. While the details may vary from model to model, each Turing model needs to include probability distributions for both the prior and the likelihood. In this case, we need to define prior beliefs for the weights, the average day of year, and some unknown factor. There are 16 weight parameters, so we need prior beliefs for all 16 weights. In this case, we're using the same distribution for all of them, which is a normal distribution with a mean of 0 and a standard deviation of 1. Because there's more than one weight, we need to use the mvnormal distribution function. For the average day of year, our prior belief is that the average day of year for the cherry tree to reach full bloom is day 100, or April 10th on a non-leap year. For the error, our prior belief is that it's some positive number, but we really have no idea what it is. For the likelihood, rather than looking for a collection of straight lines or a collection of logistic curves, we're looking for a collection of b-splines. Here, we're using the spline constructor that we used in the Pluto notebook to generate our curve. The spline constructor takes two arguments, the basis and the weights. Again, the basis is a function definition for a flexible curve, and the weights are the parameters that define a specific shape for that curve. The spline variable must then be added to the average day of year in order to fit our data. That weighted average day of year is then used as the mean value for the likelihood that we believe to be normally distributed, with a standard deviation of the unknown error factor. After defining the model, the inference step is similar to the inference steps that you've seen before in previous tutorials. Here, we're using the nuts sampler again and collecting 1,000 samples. You may need to scroll in the REPL to view the summary statistics table. In the summary statistics table, you should see 16 rows for the 16 weight parameters, in addition to a row for the average day of year and a row for the unknown error. Even though our prior belief was that the weights were all centered at 0, the posterior mean values for the weights are either positive or negative, depending on the weight. Recall that a positive weight will bend the B-spline up, and a negative weight will bend the B-spline down. Note that those last two weights are unusually large negative values compared to the other weight values. It looks like the mean value of the average day of year is consistent with our prior belief of it being between 90 days and 110 days. And the value of the error is also consistent with our prior belief that it was some positive number between 0 and 10. While we're here, also note that all of the r-hat values are close to 1, which is a good sign that our model is okay. Now let's visualize these results to get a better idea of what's going on. There are 18 sets of diagnostic plots, 16 for the weight parameters, 1 for the average day of year, and 1 for the unknown error. All of the plots along the right-hand side have nice Gaussian distribution shapes. And you can see the mean values for the weights bounce back and forth between positive values and negative values. The plots along the left-hand side are called trace plots, or sometimes referred to as hairy caterpillar plots. The trace plots track the history of the parameter values by sample. What you're looking for is a history that bounces back and forth around some mean value. So these trace plots are all good examples of what your trace plots should look like. If you see wild variations in these trace plots, that's a red flag that something may be off in your model. In any event, these trace plots all look good, so we're ready to move on to plotting our results onto the plot with our data. Click on the Julia logo icon and click on the table icon for the chain variable. In this chain, there are 16 columns for the 16 weights. Before we can plot our B-splines, we need to go through each sample and collect all 16 weights and place them inside of a vector. In the end, we'll end up with a vector of vectors, containing 16 element vectors for each sample. That R stands for regex from Julia Base. Regex is being used to select all of the columns in the data frame that have a header that contains the word weight in it. Click on the Julia logo icon and click on the table icon for the weights underscore vector variable. The weights underscore vector variable contains a single column. Each element in this vector is a vector containing the 16 weights for that sample. We now have everything that we need to plot our B-splines. Using a similar for loop that we've used in previous tutorials, we're going to add 1000 B-splines to our plot with the data. Don't forget to call the name of the plot to view the updated plots. Pretty cool, right? So, what does this plot show us? Historically, it looks like the cherry trees in Kyoto City, Japan reached full bloom every year on average around day 104 or April 14th on a non-leap year, plus or minus a week. There may have been some fluctuations over the centuries, but it's been fairly consistent. Consistent, that is, until recently. For the past 100 years or so, that is, the post-industrial revolution period, the cherry trees in Kyoto City have been reaching full bloom sooner. So rather than holding their annual Cherry Blossom Festival in mid-April, now it's not unusual to hold the Kyoto City Cherry Blossom Festival anytime between late March to early April. According to the Kyoto City official travel guide website, cherry blossoms reach full bloom in late March to early April in 2023, depending on the location in the city. In fact, at some locations, all of the cherry blossoms were completely gone by the end of March. Maybe a difference of a week or so doesn't seem like a big deal, but the trend is certainly concerning. Now, this plot is a time series plot, so it doesn't show any causal factors, and you shouldn't draw any causal conclusions from it. All we really did today was some descriptive analysis and some exploratory analysis. But it's an interesting plot nevertheless, since we were able to use Bayesian inference and the language of probability to help us better understand an intriguing environmental phenomenon. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey!